I want to give you another look at an alternate version of how you might simplify a radical. This one, instead of being based on prime numbers, is going to be based on perfect squares and perfect cubes. So we need to start out talking about those perfect squares. What are those numbers that you get when you multiply a number by itself? Well, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, 6 times 6 is 36, 7 times 7 is 49, 8 times 8 is 64, 9 times 9 is 81, 10 times 10 is 100, 11 times 11 is 121, 12 times 12 is 144, 13 times 13 could be 169. 14 times 14 is 196. So there's lots of these, and we could continue on. But if you know your perfect squares, then you might be able to use this alternate option about simplifying a radical form. If this doesn't work for you, by all means, you can still use the factor trees and work with those prime numbers. But if the prime numbers don't really work for you, or you're starting to see some other connections, this could be a little bit more of where you're headed. So I'm going to start off with this example 2 here for a square root. And what I want to do is consider my perfect squares. Can this square root be divided by any of these perfect square numbers? And so I sort of think about that as the factor tree idea a little bit. 340 can be divided by 4, which is a perfect square. So even though it's not prime, I can stop there. I don't have to do anything else on that branch because it's a perfect square. But it's 4 times 85 that I would get. So 85 itself isn't a perfect square. Maybe I need to keep trying to separate that and check it out. 85, let's see, can certainly be divided by 5, and that would be 5 times a 17. Well, 5 is a prime and 17 is a prime. So what we're going to do is rewrite this square root of 340 here so that you can see it. Once you start to see these connections a little bit, then you might not have to write it out so much. But so I'm talking about the square root of 4 times the square root of 5 times the square root of 17. So I took all of these numbers that I had at the bottoms of my branches and wrote them out into these individually multiplied radicals. Now they're still the same as the square root of 340. But what do you notice there? You've got to realize that the square root of 4 is 2. That's a perfect square, so we can write it. Now, square root of 5 is not a perfect square, and square root of 17 is not a perfect square. So nothing is going to clean those up. And like we saw on the other side with the factor tree, I don't have a match. I don't have a pair for them to pull outside, so they would stay under the radical of the 5 times 17 as 85. So this could be your rewritten form of square root of 340 is the same decimal value as 2 times the square root of 85, but we did that based on the perfect square of 4. We'll try that out again here with example 3. This is another square root, so I'm going to be thinking about my perfect squares. Is there a perfect square in that list that I can divide 180 by? Well, I'm going to go ahead and try to divide, let's see, 180 could be divided by 36. And that leaves me with 5. I know 36 is a perfect square, and I know 5 is a prime. So in my head, instead of thinking about the square root of 180, I'm actually thinking about the square root of 36 times the square root of 5. What do you notice there? We've got to recognize that the square root of 36 is a perfect square. That is 6 times the square root of 5. I can't do anything else to simplify that. It's just what it is. So the square root of 180 is the same as 6 times the square root of 5. Now, we can think in a little bit of a similar process for this if you're doing a cube root. But to do that, you've got to know your perfect cubes. Now, I'll even admit I'm a little bit rustier at my perfect cubes. 2 to the third power is 8. 3 to the third power is 27. 4 to the third power is 64. 5 to the third power is going to be 125. 6 to the third power would put us thinking about 216. 7 to the third power is going to get you going with 343. 8 to the third power is 512. 9 to the third power, that's going to be 729, or 10 to the third power is 1,000. Certainly, you could keep going with that, but you just need to be able to find something in that tree for you. So I'm looking at 1080 here on that example 5. It's going to be a cube root problem. 1080. Is there a number in this perfect cube list that we can divide it by? Well, turns out that 1080 can be divided by 8. The factors would be 8 and 135. And I'm going to put a square around 8. Even though it's not a perfect square, I'm still thinking under the same process. It's a perfect cube, but I can stop that branch there because it's in my list. Now, 135 can actually keep on going. We can break that apart. So maybe you're thinking about breaking it up into primes to see if it has any other perfect cubes. Or 135 actually can be divided by 27, which 27 is in our list of perfect cubes. So I could stop that branch there. It's actually 27 times 5 that gives us 135. And 5 is a prime, so I know I can't take that any further. So you're actually thinking about the cube root of 8 times the cube root of 27 times the cube root of 5. That's everything that we've got going on in here. So you're asking yourself, well, what is the cube root of 8? That's 2, because it's 2 times 2 times 2 that would give you an 8. And what is the cube root of 27? Well, that's 3, and I don't have a cube root of 5. It would stay just as it is. So if you've got multiple values outside of your radical, by all means multiply them together. So 6 times the cube root of 5 is the exact same equivalence of the cube root of 1080. So you have that as another option for how you might want to think about simplifying radicals. Good luck with it.